Bismillahirrahmanirrahim. Today our next topic name is Laplace transformation. In previous lectures, we will finish our lectures regarding Fourier series, and then we see the Fourier sine and cosine series, and then in the last Fourier complex series. Now this chapter relates with the topic Laplace transformation, and in this respect it is our 17th lecture. Now we start our lecture. First of all, I want to define the Laplace transformation. What is Laplace transformation? So Laplace transformation, let f be a function defined for t is greater than or equal to 0. It means for all real time. Let f be a function defined for t is greater than or equal to 0. Then the integral Laplace f of t is equal to from 0 to infinity. It is and then e raised to the power minus st f of t dt. This is our notation of Laplace. This in the floor writing. So the Laplace of f of t and the function is based on the real time, and it is equal to from 0 to infinity e raised to the power minus st f of t dt, where s is any real number. Another way that we define the Laplace transform, that is the product of exponential function, the product of the exponential function with a real time function, the product of exponential and real time function, and it is integrated from 0 to infinity with respect to t. I'm again repeat this. The product of exponential and real time function and their product is integrated from 0 to infinity with respect to t. This is also called the definition of the Laplace transformation. And you know that what is meant by the transformation. I was telling you a lot of time about the transformation. What is meant by the transformation? Transformation mean which change its shape. The thing which change its shape, transform. You see also in the movies that the transformers or the transfer in which cars are converted into robotics. And similarly, you see in your daily life the transformers which are fixed at different places on roads. Some way it is called the step down, and some way it is also called the step up. So these types of transformer based on the nature of the primary and the secondary coil. So transformation regards here in which how a function change itself into another form. Now we proceed in this way. Is said to be Laplace transformation of f provided the integral converges, or provided the integral converges. It means it gives its answer. In elementary calculus, you learned that differentiation and integration. In elementary calculus, you learned that differentiation and integration are transformed. In which you see that when you take do integrate the differentiation of a function, how it changes itself, and on integration that function change how itself, because differentiation and integration are two operators, in which one is the differentiation operator and the other is the integration operator. It changes the nature of the function. So we say these are called the transformer functions. Roughly speaking, these operations transform a function into another function. For example, when we operate the derivative on x square, when we take the derivative of x square, it is equal to 2x. So you see how it changed the nature of the function. x square to here it is a quadratic function, and when we apply the derivative on this, it change its nature from quadratic to linear one. And here you see integral of x square, here our function is quadratic function. After taking the integral, it becomes a cubic function. So in this way you also see how this integral change the nature of the function. Similarly, when we integrate the integrand over a limit, over a closed limit, over a closed integral, it gives our exact answer. Moreover, these two transforms possesses linearity property. Moreover, these two transforms possesses linearity property. This means that the transform of a linear combination means the addition of different functions in a row, or different terms in a row. This means that transform of a linear combination of functions is a linear combination of transform. Here you see that here Laplace transform of a function f of t. When we apply transformation on this f of t, it transforms this small f of t. Here the original function is f of t small. When we apply a transform, it changes the function. From small to capital, and here the dependent variable is t. Here it transforms this variable to s. Or one other example, that is the conversion of displacement into velocity. It is also a transformation, and the conversion of velocity into acceleration, it is also a transformation. Similarly, the conversion of acceleration into jerk, this is also a transformation. Another example of transformation, that is the conversion of frequency into time period, or the time period into frequency. These are the transformations. So here you see that Laplace of f of t is equal to from 0 to infinity e raised to power minus st f of t dt is equal to f of s, capital F of s. This transform this small f of t into capital F of s. Similarly, the Laplace of g of t, when we take the Laplace of g of t, it transforms this small g of t into capital G of s. And similarly, the Laplace of capital H of t. So when you transform this, take the Laplace this, it convert into a small h of t. So these are the examples of linear transformation. How to change a function into another form. So now we take example when f of t is a constant. Now f of t is a function which change its shape like let's say constant, then trigonometric, then exponential, then hyperbolic, then algebraic terms. These are different shapes of the function that it takes. So one by one I take one shape of f of t and try to explain you. Here, when f of t is a constant function, so f of t is equal to c. C takes any shape 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, whatever it is. These are also constants. So I am writing generally it is a c. So by definition, Laplace f of t is equal to from 0 to infinity e raised to power minus st f of t dt. Here I substitute the value of the function f of t, that is equal to c, is equal to from 0 to infinity e raised to power minus st c dt. This c is constant taken outside from the integral, and then take the integral of e raised to power minus st. It is equal to e raised to power minus st over minus s from 0 to infinity. So it is written as minus c over s, then 1 over e raised to, here e raised to power is negative, so when I take convert it into fraction, so it becomes positive. From 0 to infinity, when I evaluate this on the given limits, it is equal to 1 over e raised to power infinity minus 1 over e raised to the power 0. And you know that e raised to power infinity is equal to infinity. E raised to power infinity is equal to infinity. Sorry, one problem I do here, one mistake I do here, that is infinity. That is infinity. Infinity, e raised to power infinity is equal to infinity. So you make a correction here, that is infinity. Then you know that e raised to power 0 is equal to 1, so this is equal to 1 over 1. And you know that 1 over infinity is equal to 0. So this part becomes 0 and our remaining part is that is equal to minus 1. When you multiply this, this is equal to c over s, where s is a real number which is greater than 0. Similarly, if you substitute the value of c is equal to 1, then your answer is equal to 1 over c. If c is equal to 2, then it becomes 2 over s. If it is equal to 3, then 3 over s. If it is equal to minus 1, it is equal to minus 1 over s, then minus 2 over s, minus 3 over s. So these are the values you take. So now we move towards another case in which f of t is an exponential function. When f of t is an exponential function, let f of t is equal to e raised to the power alpha t. By definition of Laplace, Laplace of f of t is equal to from 0 to infinity e raised to power minus st f of t dt. Here I substitute the value of f of t, that is equal to e raised to the power alpha t. So I am substituting here the value of the f of t, that is e raised to power alpha t. Now we know that the properties of the exponential function. We know that the properties of the exponential function, when bases are same, powers add, and it becomes e raised to the power minus into s minus alpha into t dt. When you integrate this, it is equal to e raised to power minus into s minus alpha into t divided by minus into s minus alpha. From 0 to infinity, I take this negative 1 over s minus alpha outside and write this exponential function into a fractional form so that its power become positive. Now I evaluate this on the given limits. It is equal to 1 over e raised to power s minus alpha into infinity minus 1 over e raised to power s minus alpha into 0. And you know that e raised to power infinity minus e raised to power 0, and you know that e raised to power infinity is equal to infinity. So 1 over infinity is equal to 0. So I am writing here 0. Then e raised to power 0 is equal to 1. 1 over 1 is equal to 1. So when I multiply this, it is equal to 1 over s minus alpha. And I am also writing it as f of s minus alpha. F of s minus alpha. Here you see that one thing more I want to explain you, that is here e raised to the power minus, the exponential function has power minus s, then you write it as f of s. Now you see here one thing more, you note that here exponential function has power. Here exponential function has power e raised to the power minus s minus alpha. At the place of alpha, no, it is s minus alpha. At this place, at the place of s, it is s minus alpha. So you write it as f of s minus alpha. Other things remaining same. Here negative sign, you must take care with negative sign, it must appear here. You are not trying to do this this negative sign you want somewhere to make positive. It is not. It is a definition of the Laplace that this negative sign must appear here. If there is negative sign and then some multiplier with t, then you take its Laplace. Otherwise it is impossible to take the Laplace transformation. So here I am writing s is greater than alpha. Hope you understand this. Next we move another example relating to this category, that is f of t is equal to e raised to the power 60. E raised to the power 60. In the previous I am taking the general function in which e raised to the power alpha t. Here at the place of alpha we have 6. So again, using the definition of the Laplace of f of t is equal to from 0 to infinity e raised to the power minus st f of t dt. Now I substitute the function here, e raised to the power 60, then from 0 to infinity e raised to the power minus st e raised to the power 60 d of t. So I am writing here e raised to the power minus into s minus 6. So our answer is, here you see that e raised to the power minus st, other things remaining same as you see in the previous general proof. At the place of alpha we have 6. So just you substitute only at the place of alpha, you write only 6. So this is equal to f of s minus 6, where s is greater than 6. I am taking another example with the negative sign. Here you see that alpha is equal to minus 3. Alpha is equal to minus 3. If you if I asked you tell me the direct answer of this function, then what is your answer? First you take the help of its general answer, that is equal to, and if you say that if f of t is equal to e raised to the power alpha t, then its Laplace is equal to 1 over s minus alpha. 1 over s minus alpha. Here the value of alpha is minus 3. Then you substitute directly at the place of alpha is equal to minus 3. Then your answer is equal to 1 over s plus 3. 1 over s plus 3. Now you see this in this here, 1 over s plus 3 is equal to f of s plus 3, where s is greater than minus 3. When f of t is a trigonometric function, so I take here f of t is equal to sine alpha t. By definition of Laplace f of t is equal to from 0 to infinity e raised to the power minus st f of t dt. Here I substitute the value of f of t, that is sine alpha t is equal to from 0 to infinity e raised to the power minus st into sine alpha t. Now you substitute here, you know very well aware with this that the value of simple sine in a form of exponential function. A simple sine in a form of exponential function, that is sine of alpha t is equal to e raised to the power iota alpha t minus e raised to the power minus iota alpha t divided by 2 iota. Now I substitute this value at the place of sine of alpha t. As you see here, now I multiply this e raised to the power minus st with this exponential function and this exponential function. I am multiplying this. E raised to the power minus st e raised to the power iota alpha t minus e raised to the power minus st into e raised to the power minus iota alpha t. Using the rules of exponents, here e raised to the power minus into s minus iota alpha t, then minus e raised to the power minus into s plus iota alpha into t dt. When I take its integral, I get e raised to the power minus into s minus iota alpha t divided by minus into s minus iota alpha t from 0 to infinity minus e raised to the power minus into s plus iota alpha into t divided by minus into s plus iota alpha from 0 to infinity. When I check these answer on, when I evaluate these functions on their respective limits, I get 1 over s minus iota alpha minus 1 over s plus iota alpha. When I take its LCM, I get 1 over 2 iota into 2 iota alpha into s square minus iota square into alpha square. And you know that what is the value of iota square is equal to -1. So it becomes 1 over 2 iota into 2 iota alpha s square plus alpha square. This iota, 2 iota is cancelled with this 2 iota. We get alpha over s square plus alpha square. So remember these formulas also. You have somewhere to substitute direct their answers by using these proofs. So Laplace of sine alpha t is equal to alpha over s square plus alpha square. Now I take an example relating to this case. Laplace of sine of 60. Here you see that at the place of alpha we have 6. At the place of alpha we have 6. I am using general rules here. So Laplace of sine alpha t is equal to alpha over s square plus alpha square. So you only substitute at the place of alpha is equal to 6. I am doing here. Sorry. You see here, put alpha is equal to 6. Laplace of sine 6t is equal to, at the place of alpha you substitute only 6. You get 6 over s square plus 6 whole square. This is equal to 6 over s square plus 36. This is our direct proof of sine of 6t. In the same way, I am taking another trigonometric function, that is cos of alpha t. By definition of Laplace, I am writing here its formula. Then I substitute f of t is cos alpha t is equal to from 0 to infinity e raised to minus st into cos alpha t. Again I substitute at the place of cos alpha its exponential function, its identity in a form of exponential functions. This is equal to e raised to iota alpha t plus e raised to minus iota alpha t divided by 2. In cos there is only 2, but in sine it is 2 iota here. Don't mix these identities with each other. So from 0 to infinity e raised to minus st, then write the formula of cos alpha t here, e raised to iota alpha t plus e raised to minus iota alpha t divided by 2 dt, taking 2 outside and then multiply this e raised to minus st inside. You get 1 over 2 from 0 to infinity e raised to the power basis same, parts add. Then I take the integral and after evaluation the answer on their given limits. Our answer is 1 over 2 into 1 over s minus iota alpha plus 1 over s plus iota alpha. Now I take the LCM of these two. So I get 1 over 2 into 2s into s square minus iota square into alpha square, and you know that iota square is equal to negative 1. So it becomes, this 2 is cancelled with this 2, it becomes s over s square plus alpha square. So the proof of Laplace cos alpha t is equal to s over s square plus alpha square. So what is the difference between the Laplace of sine alpha t and Laplace of cos alpha t? Here you see that when we derive the formula of sine alpha t, here it has the angle. So when you get the formula of cos alpha t, here at the place of constant u has s. So these are the two distinctions between these two formulas. Here the angles involved, here the real numbers involved. Okay, this is our first lecture regarding Laplace transformation. Inshallah we will meet after some time with another lecture on Laplace transformation. Okay, take care. Allah Hafiz.